Okay, so this is problem 6 from mathematical circle. So this is problem 6 in invariance. Let's see what the problem is. So this is again, we have a chessboard. So I'll just first say the problem verbally. So there is a 8x8 chessboard. Okay. And only one of them is colored. So one of the boxes is colored black and everything is colored white. Okay. Now prove that one cannot make all the boxes white by recoloring the rows and columns. Recoloring means that the entire, if you're recoloring a row, then the entire row, the colors get switched. Okay. Or the entire column, the colors get switched. Okay. So this is a very sample problem maybe of a whole variety of questions. So let me just write it also. So there is a 8x8 board. Yeah. One cell or one box is black. Okay. Others all white. So this is the initial state. Okay. So this is the way we have been writing the problems. This is our initial state. Okay. What we are allowed to do is each move. Yeah. We recolor a row. Okay, means to change the color of the row. Or if it's black, make it white, white, make it black. Okay. Each move, recolor a row. Or a column. And the state we are questioning, okay, can we make all white? Well, in fact, they are asking us to prove that you cannot. Okay, so which will be evident once you try. Even if you try for 4x4, it will be clear. So let's just do it for 4x4. Okay, it doesn't really matter. So let's just do it 4x4. So I'll just no, one box is black and everything else is white. So this is not your usual chessboard. Okay, so it's just a 4x4 board which is colored like this. So yeah. So I'll just show one or two moves and then I'll ask someone to maybe, yeah, I'm sure someone can do this. Yeah, should be able to do this. Let's see. So we have this and any box can be black. So for example, this one is black. Okay. So then if this one is black, then and everything else is white, right? So let's say that you do R3. So by R3, I mean you change the state of row 3. Okay. So then what will you get? So this is, so what should we get after doing R3? Apart from this, what others will be colored? What other cells will be colored? Yes, the entire third row will be black. Okay. So this is how it is. And but let me show one more, or let me ask one more. What if we do C3? So C3 means third column. What board are we going to get? What coloring? Same question. It's given that one box is black and others are white and that makes sense. Sorry? No, sir. Yes. The one condition is that, not in the question is that both correct board one is black and the others are white. And what's the next? Which is, no, that is what the move is. So in every move, you can recolor a row or recolor a column. Okay. Yeah, that's so. Is it clear? Yeah. So you can choose your row and your column and do that. If we do C3, so Ishana, you were saying, so what will it be? I can't hear you. Top, say again. Yeah, the other two will become white and these two will remain black, right? This is obvious. So this is what we get. Now, why can't in this way, why cannot we make all of them white? Yeah. So Pragdish, do you understand the moves? Okay, nice. So now you try to see why is it that we cannot make everything white? Today the light is a little dim. I've shifted to a darker place a little bit. It's the same room, but it's night time. It's too bright. Then after teaching, I can't sleep. My eyes get. I try to make it in the morning, but it is not possible because I think people have school and some other time zone. Yeah. Anyways, what will prevent you from making everything white? But yeah, please explain more. You may be able to see it, but you have to. So why one blocks will remain black? At least one. I mean, for example, if I make an entire column black, then in the next move I can make everything white. So I had blacks, but then I got everything white. Right? So you have to say a little bit. There's a little bit more. The invariant is that no matter how you color them. Hmm. Okay, so your claim is that number of, let's say, black boxes is always odd. Yeah, that is correct. But this much is enough. So how do we prove this? Yeah, that. So let me say to everyone that what he's claiming is that at each stage, the number of black boxes is an odd number, which you can see in these three, right? At each stage, number of black boxes is odd. Does everybody feel this is true? Now, how do we prove this? How do we argue this? That is, we started with odd number of black boxes. Is that what you said? Ah, but if this one has to say more, because all of us know this, that we started with the odd number of black boxes, but then that will, there has to be some simple logical steps with which you have to arrive. Yeah, see, this is the thing. You see, we all can feel this, but we need to be able to explain this. Right? What is it that is keeping So this is the key things in invariance principle. What is invariance principle all about? Studying a complicated phenomena, which is several steps and several possibilities, right? Studying the steps of it, understanding this thing by understanding what can happen when you go from one move to the next move. So try to analyze that when I'm at a certain place, arbitrary enough, because obviously if you are at this initial place, then you can see that it will be remaining odd. You can see that if that cell is anywhere else, that black cell is anywhere else, I apply the move, I'll get an odd number of black cells. But try to understand step, right? So if I'm at a place where there are odd number of black cells, draw arbitrarily odd number of black cells, and then see if I make a move, then why will I again have an odd number of black cells? What column am I affecting and how is it? Understand one step. That is what invariance is all about. So try this is to think. Mm-hmm. Say it again, because you said two black boxes. Say it again. So did you say, you said two black boxes? So where are two black boxes or? Uh-huh. Yeah. But you're right. I mean, because every move is very simple in some sense, right? It's arbitrary, but it's simple. There was a much harder version of this problem, which someone had asked, I think Unab had asked, but I could not do it. Some TST problem, very similar problem. What was the initial state? I mean, this move was the same, but what was the initial state in that problem? If you remember, so it was the same thing that we have to pick a row and we have to switch the colors, right? And pick a column and switch the colors. And finally, we have to make all white. But the initial state was much more complicated, right? If you remember it, you should tell me sometime. But we couldn't do that problem. But anyways, this one is easy. This one is much easier. So you try to explain, why, like if there is an odd number. So let's say that if I just let's start with this. Just make this and try to explain why, if I pick any row or any column, and apply the move, why will I again get an odd number of things? I mean, one can obviously check it. Like if I pick the first row, then this will become black. So we had one black and now we have three blacks, right? So we have two blacks more. And so obviously it will remain odd. Oh yeah. Hmm. And even so when you recolor, let's say you recolor a row. So if I'm recoloring a row, so explain me like this. So if I'm recoloring, let's say the second row, and let's say my second row had, so let's say I'm recoloring the second row, then how would you explain? But then it will be more rigorous. So that's why I'm trying to make you explain like this. So oh, no, no. Okay, so in this case, but in this case, you are saying that everything is white. Yeah. So yes, I mean, if you're recoloring, let's say the second row, and if there are an odd number of black boxes before, right? So let's say that there are odd number of blacks. Okay. And you're recoloring the second row. If the second row has no blacks, so you can do this casework, right? If the second, just do casework. If the second row has no black boxes, then how will the number of black boxes change? Just +4. Is that right? So odd +4 is odd. But you can do the other casework also, right? I mean, if there are 2 black boxes, it doesn't matter where they are. If there are 2 black boxes, then what will happen? Then it will be +2 -2, right? Or rather, yeah. So the 2 blacks will become white and the 2 whites will become black. So it will not change, and so it will remain odd. And similarly, you can reason. If there are 3 black boxes, you can reason in the same way. Yeah, -3 +1. At each stage, the number of black boxes is remaining odd. Yeah, the parity of the number of black boxes is not changing. So, I mean, that's what Ishana said in the beginning, because we're starting with 1 black box. That's why odd number, so it will remain odd. But the explanation has come now, kind of, through our efforts. So does everybody understand the argument? So this is the kind of argument, if you've never done before, then it can be a little tricky. But first step is that you have to work out quickly, energetically, work out a lot of examples, and at least you see some pattern and you make the right claim. That one should be able to do. That's the first step. Yeah, if you don't put in that energy in the beginning, then all strategies will not, no strategies will work. And then these strategies which you are learning, yeah, even if you don't know now, you know, yeah, that this is how we show parities. Parity is invariant. Okay, so if there are any questions, then please say. Right, but that is not sufficient. Yeah, even if one row is completely black, that does not imply you can make all white. Yeah. But really, you see a very interesting thing here, that we have used the fact that every row has 4 things, that every row is even and every column is even. Both, right? That is very important, right? That every row has an even number of items and every column has an even number of items. That is fundamental here. Yeah, because every time you see the reasoning is like that. So this problem will be true in 4/6 also. You should do the reasoning. Yeah, you should try this out in 4/6. So 6 is the number of columns, right? So if you pick a row, it has length 6. And then you have to do the same kind of argument. If there is 1 black box or 2 black box, you can do shorter arguments also, but just do it like this. Now, if you have 1 black box, then what happens in that row? If there are 2 black boxes in that row, then what happens? Yeah, and you see. Okay. Fine. Now here is a slightly more challenging question. So as I said, this is a whole theory, and this is a whole let's forget theory. There is a whole class of problems that are very, very approachable. Okay, very, very approachable, and sometimes they're very, very difficult, in the sense that they're easy to understand, but sometimes they can be very difficult, and also sometimes they can be just done by a very clever way. Okay, so especially for the younger, like suppose someone wants to do a little bit of original work. So I'm not calling it research, okay, but want to do original work, like if you're in high school, because just preparing for Olympiads is good, but if doing original work, like even those who are in CS, right? These are the topics. These are the topics that you can look at. But obviously, first you need to be good at the basics, like you need to do these things, basics, solve like 100 problems on chessboards, like these simple ones. Then you can enter into very interesting problems. So if someone shows interest, then I can try. I'm planning that maybe after some time, every week, one person can do presentation. That will not be a class. That's not a class. That's just I will sit and listen. Everybody will listen, and that's all. It's not a class. It's just someone. So I will ask someone to maybe read something or think about. So I'll frame the question things in a way that you can, it will be accessible to you, and then you will read, means something very simple which maybe I can know but I don't know, and you can easily read it and tell. Okay, I will start to almost started to do that. We'll do it at in the other class after this month. The exam gets ISA entrance is over, but here also I should do, because a lot of simple things which you guys can read and think and play around and present. Okay, and that will be very very good. Okay, so that will certainly will do, then that will be much better. Okay. So I'm saying, just saying that these are the topics that, you know, in chessboards a lot of scope is there, because there is no big language to learn and so on. Like you see, once we did that, uh, can every odd number be obtained, something like that, right? We had numbers on a board. So now that's a problem which is not a known problem anywhere. Like obviously, I mean, any decent mathematician can, I mean, anyone can do it. That's not the thing. But I mean, yeah, you can do it on your own, and it's your own thing. It's a good thing. You can present that, and then slowly it becomes more and more original. Now the question is, if there is a 4x5 chessboard, then is it possible? Yeah. So, and this is the homework. You can try this. So is it possible to make all white by, you know, by same moves? By the moves that we mentioned, is it possible to make all of them white? Okay, so just think. Yeah. So a lot of coloring problems come to my mind that you guys can access, try to think and read, maybe some monthly, some you can read and present. And there are other things, like there are proof without words. Those certainly, you know, people below 10th grade can easily, I mean, you guys are not below 10th grade in that sense, but yeah, easily you can do. Okay. So, and maybe other more advanced people can break down certain topic and explain to us. That will be good as a presentation. Okay, so think about this problem, and then let us move to the next one. Yeah. So now you see there is another problem, problem 8. Okay. Oh no. So this is slightly different. So let's try this. Problem 8 is slightly different. I think I don't know how to do this. Oh, problem 7. Sorry. So solve the same problem in 3x3 if initially there is only one black box in one corner of. Okay. So now there is one black box, but now it's in the corner. So let's think, I don't know how to do this. So this is problem 7. So we have the same moves to make, and same problem, can we make everything white? So in this, can we make everything white? Oh, in this also you cannot make everything white? Good. Okay. How? Write the question. Okay. So why do you think we cannot make everything white? So moves are same, everybody. Okay, the moves are same. So I'm not saying. So I don't know. So making everything white is the same as making everything black. Okay. So this is the same as making everything black, because if you can make everything white, then you can make everything black. And if you make everything black, you make everything white. That's clear, right? So same as making everything black. But then why can't we make everything black? So others can think of this directly also if you want to. It's a bit tricky because in each move, if there is initially there is one black, then after one move, you will get 4 blacks or 2 blacks. So the parity of the number of blacks becomes even, but then again it becomes odd, and then again it becomes even, right? So there's no guarantee just in based on parity that you cannot get 9 blacks. But maybe some other argument we can use. I don't know. Let's see. This is a tricky question. So any ideas? Why can't initially I would have thought it's possible, but then yeah, it seems like it's not possible. Okay, but does everybody see that only arguing with parity will not enough, right? Because like we have one, as I said, we have one black. In the next move, you can get 2 blacks or 4 blacks, right? Like if you choose this column, then you get 4 blacks. But then again, you get, again you choose this column, the last column, you get 7 blacks. So you're getting even number of, so you can get odd number of blacks again. So maybe it's possible to make all blacks. And similarly, if there are 8 whites then in the beginning, but then you can make odd number of whites. But it's not just odd and even. There is more to this problem. So is it because no, we don't have to have same parity because 9 blacks and 0 whites. Right. So yeah, that's a parity itself. A parity on the whole board doesn't seem to work. So let's make a few moves. So can anybody tell me what first move they want to make? Just say, make the move. You can recolor row 1. Okay, so let's do that. Let's try to notice something, some pattern one has to notice, which, center. So this is not center. Yeah, that's correct. That might be possible. That is, so you better tell us. That is a good thing actually, since you have done it. So if center is black, then how do you get all black? That's okay. Okay, so let's take that only. Yeah. Good. Mm-hmm. And this is, no, this will also not be possible. Right, because you see from, yeah, right. Because it's similar situation. I mean, these two are the same problems, right? Oh, no, no, sorry. No, let me not know. No. So I don't know. Ah, ah, good. Right. No, wait, what happened? Yeah. So you get this, and then you get this. Oh, sorry, say it. I just missed it. Say it. So you can do that. Okay. Then, yeah, so I don't know. Yeah. Okay, leave it. So yeah, I don't know. We will think about it. But yeah, the positioning matters. Yeah. So if what you're saying, it might be, but I think it is not possible. Okay. But I don't know. Yeah. Mhm. Parity is not the same, and initially also parity is not the same. No, no. So if you want all to be black, then that means that black and white have different parity, right? Because 9 and 0. Right. So see, so initially, what is the parity? Initially, it's 1 and 8, right? Yeah, and eventually you want 9 and 0. So why is this not possible? I mean, just based on parity. Uh, does everybody see that the parity itself is not enough here? Okay, you have to use. See, look at the question also carefully. They have said corner square. Certainly, it matters. So we have to do something with the corners. Think something about the corners. Think about the corners. So let's make R1, let's make the move R1 and look at the corners. Read the question. That's the thing. We don't have to be very clever, like, chessboard type thing, but read the question carefully enough. We get this. Focus on the corners is what I can say, as much as I can see now. So initially we had one black in the corner. Now also we have one black in the corner. So the corners are, say, oh, overlapping. Yeah, something like that. But you have to put it in, yeah, more better words. But it is something like that. That is what I was initially thinking. So it seems like that we will always have an odd number of blacks in the corners, right? It seems like that among these four corners, we will always have an odd number of blacks, because you can see that there is one black and now again there is another black. If in the next move you pick this, fine, but the corners are not affected. Now so whenever you pick a corner row or corner column, then only, right? So if you pick a corner row, like, I mean, if you pick this, then again, no, but you see, then I'm wrong, right? No, I'm not wrong. Yeah, it's right. Because again, we get 3. Okay. So the claim is, and now this is homework because I can see it's easy to prove. You can again just take a situation in which there is an odd number of these things in the corner and take the move. Yeah, the move, if the move is affecting a corner row or corner column, then only it will affect, and then you can just see, right? It just changes the pages. Yeah, you can just see. Yeah, this is simple. So think about it. If you cannot, then you should ask me, but you should honestly think about it and then you should ask me. Okay, don't you can also ask me later and after the, but ask me, but to clear it out if you cannot. Okay, but this is the claim. Claim is that corner, so odd number of odd number of, I think I'm speaking too loudly, right? Odd number of columns, so corners, odd number of corners are oh, what am I doing? Are black. What is the order? Odd number of corners are black. Okay, so this is the claim and you can see it. So I didn't know how to do this, but just reading the question clearly and just seeing the pattern. Okay. Right. Well, this will go into some coloring strategies later on. You will see, I think, where they will say that you paint the corners red and then something special happens and so on. And but those are not needed here. This is special enough. But yeah, basically there is a certain subset. So the whole thing is not an obstruction, but then there is a certain subset of this pattern, you know, of this whole 9 things, right, which creates an obstruction. Do you guys see this, right? There is a certain subset which creates the obstruction to the entire thing happening. And figuring out that subset has to necessarily be strategic or artistic, because you cannot figure it out by brute force, because there are 2 to the power n subsets, right? You cannot do it by brute force. So like a machine cannot do it. That's why these are problems, right? So a machine cannot figure out, you know, this kind of obstruction directly. Now, obviously, some randomized different things, but you know, thinking traditionally, I'm saying that this is a human kind of thing, yeah, because there's an exponential number of possibilities the obstruction could have come from. Okay. So yes, exactly. No, that's right. So that's what basically I've also said, that odd number of corners are black means that there can be at most 3 blacks in the corners. Right, and then the rest of the reasons. But yeah, but once we say odd number of corners are black, it means that at least one of those have to be white, and so all cannot be black. Okay, or you can just say that odd numbers of corners are white. Same thing, doesn't same thing. So yeah. Okay. So you see, like this did not involve any theory, right? Now there could be some problem in which instead of corners, yeah, some pattern would be there in some other, you know, some other kind of place. Maybe, I don't know, maybe center, or just center in itself not be enough. Maybe something, maybe this, I don't know, right? Something somewhere. So you have to really watch out for those things. Some very interesting colorings are there. Okay. I am very bad at these things. I don't know, but those people who do these things, you know, combinatorics without words, proof without words. If you Google these words, you will see. Well, maybe not proof without words. Proof without words is a huge, big area, but no, this tiling problems, elementary ones. You see, there's some ingenious things out there. Okay, but yeah. So just did this small problem. Okay, so let's do one thing. Okay, so there is another chessboard problem, but let's not do that now. Okay, let's not only do chessboard stuff. I just wanted to do one more type of thing about numbers and digits, because that's another, because there is something simple I find here, which I suppose all of us can appreciate. So I know the question, but I will still share with you this link. So usually I don't do this like random Google thing, but this one was pretty good. Okay, so I'm not just pretty good; it's very accessible. That's the whole point, because there are many good things. There are books written on invariants. Okay, invariants and monovariants. So there is an interesting thing. So if you Google it, so you will get something like code forces. Now I have nothing to do with coding, but you can see that there is, okay, so I have to just share it once. Just give me 1 second and share it and show it. Because then because there are other problems which I will not be able to discuss now. So you have to try it on your own. You guys can, check this out. So maybe just here. So there is this, you see. So there is this invariance and monovariance. Okay. So, okay, I should not click on it. Yeah, it's the same thing. Yeah. So how did I get this? I just Googled obviously just Googling, you can get lost because you can see the next one is pretty complicated. This one is obviously very good notes, very, very good notes, but it's pretty hard. You will not be able to, I think, follow it now. Okay. And then there are some YouTube videos. I don't know. I've not watched any of them, so I can't say. Yeah, and then it's easy to get lost because there are so many things. Okay, but once you know more, you will not get lost, I hope, after you do few more. But this one is very, very accessible because it's like a CS thing. So it will not be too much maths, so it will be very accessible. So this problem. So I'm going to discuss the first one. So I'm not going to show it that to you. But second one is easy. It's easier. Third one is so just maybe one or two you can try. And you can basically read. And this fourth one is pretty decent. It's not hard actually. After that, it's pretty hard. Okay, but yeah, you can just try it. Yeah, and this is a 1.3 is also simple. So you will see some of them will hard, some of them simple. You can just keep trying them. Okay? And if you don't understand something, you can ask. These are bonus things. You have to do this because I mean, just 2 hours a week, I can't do much. Okay, so that's you just Google in the code forces. It's very good. Yeah, but now let's just discuss this one question I want to do because I've not discussed this type of question, so I just want to discuss it. Yeah, so this is basically divisibility and invariance. Maybe I can say divisibility because we did some divisibility and pigeonhole principle, not and invariance. So we have numbers, just any numbers, it doesn't matter. So we have numbers from 1, 2, 3 till any point. So let's say to 1,000. Okay, 1 to 1,000. Okay. So what is it? So the move, each moves is you pick a number which is there on the board and you replace that number by some of its digits. Okay, so very interesting. Maybe replace so I mean just pick a number, I have to say. So pick a number. Okay, replace it by the sum of its digits. This is what the move is, and you keep doing it. Yeah, so keep doing till you cannot do anymore. So maybe that's not going to write it because it will obviously stop, right? Because at some point all the numbers will become less than 9. You guys see that? Yeah, it will be less than or equal to 9, right? So I mean, you can take any number. So let's say you take from 20. I mean, even if you take from 2000 to let's say 2000 is too say, let's say 234, 235 till 240. You take these numbers, you replace them by sum of the digits. So if I pick this first one, then what will I have? 4, 3, 7 and 2, 9. So I'll put 9. If I pick 235, then I'll have 5, 3, 8 into 10, right? And then other numbers. Now again, 10 also I can do. So 10 if I do, then I add, so I replace it by the sum of its digits. So 1 plus 0 is 1. 9 will remain 9 and so on, right? So I keep doing it. And what will I get? I'll get numbers from 1 to 9 in the end, right? Is it okay? So, so in the end, I will only have numbers from 1 to 9. Hmm? Yes, yeah. With repetitions. So 1 to 9 with repetitions. Yeah, you will have with repetitions. So here the numbers can repeat, right? Repetitions. So for examples 1 and 10 will both end up in 1. Yeah. So the question is, yeah. So the question maybe thinking what to say here. So the question can be which number appears most times? Yeah, maybe which number appears the most? This is a good question. Okay. But if there are two numbers which appear equal number of times, then that's also fine. You can say both. Or maybe let me not say which number appears the most, just say which number appears least. That's just a more cool question. In the end. Okay. So you can take your numbers from 1 to 20 and do this and see. Okay. And so, yeah, there are a lot of things. Think first, then I will say maybe. Yeah. So one thing you can notice here that there's not much mixing going on in this problem. It's not like those previous questions on the blackboard where you are mixing the numbers. So it is much more straightforward in that sense. Okay. Okay, so you think 1 appears the least. Okay. Okay. So then you guys have got it. Okay. I think. Okay. So maybe I got the question. So I should have just said most and then you could say 1. Okay. Sorry, sir. Yeah. Okay. So 1 appears the most. So, okay. So then you guys can see it. So let me not, and maybe, I don't know if you have explanation, but let me, so let's keep the homework. Okay, prove that the number 1 appears the most times. Okay, all of you can try this for me. Just try it. Okay, it's a very simple question in the sense that all you have to do is see some pattern, right? So if you, because there is no mixing here, right? 1 to 9 they will go as they are. 10 will go to 1. You can see 11 goes to 2. 13 goes to 4. And it cannot go to anything else, right? Because it's just a, yeah. But you have to explain those things. That's a different thing. But you can see the pattern and answer this question. Okay, please try this, but with explanation you should try. Okay, so that is important. With explanation. Okay, so you may have to think some numbers and number theory. Okay, so giving the answer is one level. You'll get maybe half the marks, so 40% of the marks, and rest explanation is needed, obviously. So think about this. This is there. Yeah, so this is one question. So let's not do the other questions. If you can try this there. Uh-huh. Uh, Though but there is a much, yeah, this is a pattern. There is another simple pattern like this, simple, because basically it will just be 1, 2, 3, 4 till 9, then again 1, 2, 3, 4 till 9, then again 1, 2, 3, 4 till 9. It is just 1 to 9, just, but you have to explain that pattern. That is also very important. Okay. Yeah. Never mind. This is fine. Yeah. So there are so many questions which I want to do, but I'm gonna decide which one I should do. Let's do one more chessboard problem. Okay, so that will be good, right? If the base is base, okay. So if the base, but which number will that be? So obviously there will be some number which will appear the most, but obviously that is always true because there will be a maximum. There could be two numbers that appear, yeah. But something, yeah, not 100 times more than that, but one more time, yeah, that's right. But if these numbers were written in bases, in a different base, so there's just maybe an aside question, but so I maybe you guys, if you don't know what number bases are, but that's just in thinking. So if these numbers were written in, so let's say these numbers were written in base 4, and then if you replace them by the sum of the digits, no, things can, I mean, there will obviously be a maximum. That's okay. That's set theory sets, but figuring that out might be challenging. Yeah. Okay. Yeah. So that might be a little challenging question because 9 has this very good property, right? But this is some of the digits. But if some of the digits are in a different base, then yeah, then it can be very different. Okay. Yeah. I don't know. No. I think you're right. Yeah, I think you're right. It'll be the same thing. Just the roll of 9 will get replaced by some that number less than the base, right? That can be said. So you can try it. I think it will be the same. So yeah, you're right. You're right. Similar. I mean, the argument will also be similar to, but first we'll try to argue this and then you can see that will also be similar. So let me just do one question which is based on chessboard. So this is a slightly maybe a different question. Okay, so yeah, but it's on chessboard only. So I just want to do this. So so let's say that you have a 10 by 10 chessboard. Okay, or let's not say 10, but let's say 6 by 6 chessboard, or just a 6 by 6 board. Okay. Now the question is, can this be colored? There is, yeah, can this be colored by tiles, or these are called dominoes, tiles of the tiles of the type, you know, like this, which have 4 these things. Okay, so let me maybe first kick it different. Let's say that if this was a 6 by 3, so we have a 6 by 3 board, and the question is, can this be tiled? Can this be tiled by tiles? Colored by tiles also fine, maybe so a little bit. Can it be tiled by tiles of this type? Yeah. So tiled means that, I mean, you cannot overlap, obviously, right? It means you don't want to overlap the tiles on the floor. So it will be. Okay, so you can see this is ice. Yeah. Can you tile this with these things? Yes, a tile means can you cover them with these things? So maybe you can color these red. Yeah, so you can maybe try placing one here like this, and then something, I don't know. So you have to think. Or maybe this already looks too small. Yeah, so maybe this looks too small, so you can just say no, but let me make it 9 maybe, and then you can think. I'm not going to draw everything, but just. This is one time. No, this is one piece. Yeah, so these are the pieces. You see, these are the pieces. So we can't break the tiles, though we do that when we floor the tile sometimes, but let's say we can't break the tiles. Okay, so these are the pieces, right? And then the question is, can you? So, okay, so first just tell me for this 6 by 3. Yes, right. So that's a very simple reason, right? So this is 6 and this is 3. So this means that there are 18 cells, right? But this will mean that there are 4. This is covering 4, right? So if you use 5 of them, then it will cover 20. If you use 4 of them, it will cover 16, right? So it cannot cover 18, right? Because 4 does not divide 18. Yeah, is that okay? 4 does not divide 18. So certainly this is not possible. That's a simple thing. But so well, does everybody understand this? Yeah. Is it okay? Okay, fine. That is very simple. But now you can try to do this for 6 by 6. That's a more interesting question. Yeah. 6 by 6. Now it is divisible. So can we cover this thing? Ah, good. Okay. So the answer is no. Okay. So then that's very good. Two people already think it's not possible. Oh, well, you can see first thing that tiling is much more than just picking 4 cells and coloring and blocking them or covering them, right? These 4 cells that we are covering are adjacent. Okay. So tiling is more than just 4, just divisibility. It's much more than just divisibility in that sense. So that's why even here you can see that there are 36 of them. So one can say maybe that you take 9 tiles and so I'll sell you. If someone doesn't know math, they just buy 9 tiles and come back, right? I'm just saying, they say, yeah, this will work. But 9 tiles do cover 36 cells, but they will not cover this 6 by 6 thing. Okay, they will cover 8 by 4 thing, some or whatever 36 you can get in some other way. You can think so you will get 4 into 9, yeah, that will work 4 by 9, but 6 by 6 does not work, So if someone has explanation, then you could try to say, or is it just a thought? We cannot cover, yeah. So yeah. Mhm. Right. That's okay, but that doesn't mean that this is not possible. That itself doesn't imply this is not possible. Right. Yeah. So you are saying that a simple tiling is not possible, and hence no tiling is possible, right? So let me write this thing. So because this is actually a pretty deep thing. Yeah. So certainly, I mean, this remark which you may just you say, and maybe it's also wrong, but it turns out to be correct in this case. So certainly, a simple tiling is not possible, right? So like a well-aligned tiling is not possible. That's clear. I mean, obviously, just if there are four, then we cannot place the other four here. And even like a relatively simple one is not possible, right? If you try to place the rows and then the columns, you'll see it is. So maybe some complicated tiling is possible. Yeah. So, but this, does it imply that no tiling is possible? Logically speaking, no. Yeah. Logically speaking, it is no, because you can always have all sorts of strange tilings. Okay. But there is something about tilings, you see, that if there is one complicated tiling that is possible, then I'm not making any claim that it's just a motto. And if one, even though maybe I should look at some things in this area just to understand this statement. But what I feel is that if some complicated tiling is possible, right, some complicated this and then this and then this, then because there are the symmetries of these squares, right? So there are symmetries, you can rotate and reflect. By these symmetries, we can simplify the tiling. Some shifts, some shifts, we can simplify the tiling into a simple tiling. Yeah. I feel that because of the symmetries of the square, if there is a complicated tiling, then there will be a simple tiling. Now, this is just a philosophical comment, a little bit. Yeah. So if you don't follow it, it's fine. But just my thought, right? That this is, if there's a complicated tiling that is possible, maybe this is a thing which I will certainly note down. Okay. And then this maybe I can try to carry this in my head, just in the sense that when the next time I see some tiling paper or something, some discussing with someone who does these things for living the research, then this will be, I can understand. Okay. If this motto matches with what they do, that's how math works in like some. So that's what I feel. And there's another reason why I feel that complicated tiling should imply simple tiling, is that there are in fact many tilings. So the number of tilings, if there is a tiling, then there are many tilings. There are many tilings. So there is a theorem that is also there, counting the number of tilings. That's why I feel. And in this case, that is certainly correct. That because the simple tiling is not possible, it implies that there is no tiling. But obviously, we have to give a reason. We have to give a reason. Yeah. We have to show that no tiling is possible. Yeah. But show that no tiling is possible. So anyone has ideas how you could show that no tiling is possible? So 8 boxes, I didn't understand. Where, like, why will 4 boxes be left? Okay. So if you use 8 tiles, you're saying that if you use 8 tiles, then 4 boxes will be left. And you're saying that they won't be in one row or column. But what is the reason for that? And that is, do you have a reason for that? That is, yeah. And so once again, you see there are many possibilities to try out. That's why we cannot go for a direct proof. We kind of have to find an obstruction. Find an obstruction. Yeah. So here we will see the effect the tiling has on the board. So this is a little complicated. So point is, what we will do, this is just a bonus thing. So yeah, don't worry, this is a coloring topic. Yeah. My point is that what I will do is I will color, rather I will number, and I could have colored, but I'll just number. I just number these things like this. Okay. And you can see how I'm numbering. There is nothing special. And so on, right? So what will be the next number? 4, right? 3, 4, 1, 1. And then this will be again 1, 2, 3. This will again just be the same as the first row. So do you see the way I have colored, or rather numbered, the cells? Yeah. So you go along any row to the right, it's 1, 2, 3, 4, or if it stops, then it cycles back. And similarly along every column. Yeah, it just goes forward or cycles. Okay. And now, so is it clear that this coloring? Yeah, because here we can understand the interaction of this putting a tile with this coloring or with this numbering. So we have this numbering on the board, the 6x6 board. Now you see when you place a tile, then what does it do? That's the beautiful thing about a tile, right? When you place a tile, it covers 4 consecutive rows, 4 consecutive cells on a row, or 4 consecutive cells on a column. That's the thing about a tile, right? And that I will capture here. Why? Because if I put a tile anywhere, let's say I put it here, what is it doing? Can you see something interesting? It is covering 4 distinct numbers. Okay. So no matter how you place a tile, it covers 4 distinct. So we are bringing that feature of the tile, that what a tile does. In words, everybody knows it, right? Everyone, you can tell them that a tile will cover it's like on the row or 4 on the column, and everybody understands this. But how do you capture this thing mathematically? By numbering it like this. That's one way. You see, okay, this uniformity, you encode them in numbers. Numbers are not just a way to calculate things, but also these things, right? So if you put the tile in some other way, then also you see, I mean, it should be clear now, no matter how you place them, it will cover 4 distinct numbers. Everybody sees this, yeah? Every tile, this is all, this is your hint, okay? Every tile covers 4 distinct numbers. Now you can think. Yeah, but that's uh, that's a big statement. Yeah, that's true actually. But how do you? That is true. But how do you say that? That is certainly true. That's actually a theorem, and it's if and only, and obviously it's if and only if, like, yeah. But it's a necessary condition that we should have that. So what you're saying is that for a tiling to be possible, at least one row or at least a row number or column number should be a multiple of 4, right? But that is true. But how do you explain that? Or yeah, and in fact, the explanation will follow from here. But I was not looking for that. But if you can explain it, then this is also covered in that. Think. Has to do. That is certainly correct. Yeah. But let's just think about this. So if there are 4 tiles to cover, or you can think that that's much more cleaner to think that. But if you have 4 tiles, so if everything covers 4 distinct numbers, every tile covers 4 distinct numbers. Yeah, every tile is covering 4 distinct numbers. That is certainly correct. Yeah, that is certainly correct. But like one thing is much more simpler, like is similar maybe. Yeah, is that 4 distinct numbers means that there should be equal number of ones, equal number of twos, equal number of threes, and equal number of fours. Is that right? If we want to do a tiling, then in this there should be equal number of ones, twos, threes, and fours. Right? So does everybody see this? Una, do you see this, Pragdish? Like for a tiling to be possible, there should be equal number of, yeah, or if you want, I should explain this. Equal number of ones, twos, threes, and fours. Because every tile is taking one number. Exactly. Every tile is doing that. But you see that we don't have equal number of ones, twos, threes, and fours. Okay, we don't have equal number of ones, twos, threes. You can check it. Okay, and Nagesh, you can try to prove that if one of the rows or columns is not a multiple of 4, then you will not have equal number of rows, equal number of ones, twos, threes, and fours. In general, yeah, that's true in general. So yeah, you can. It's kind of obvious, but you could obviously do the But you want us to write it, otherwise. Okay. So yeah, that's it. That's what it is. This is a slightly hard. This is not hard, but I didn't plan to do this. But we just will always do this. Okay. Yeah. So yep. So that's what. So you can kind of see what I'm trying to convey to you guys, that